Okay, let's unpack this. Have you ever wondered how scientists actually predict how molecules move or, interact?
Mm.
Maybe even how a new drug might bind to a protein.
Yeah, it seems almost like magic sometimes.
Right. But it's not. It's a really powerful technique called molecular dynamics, or MD simulations.
Hmm.
And today we're taking a deep dive into MD, specifically looking at it through GROMASS, which is, well, one of the most popular simulation packages out there.
It really
We're
is.
not just talking about what it is, but really digging into the why and the how we unlock the atomistic behavior of these molecular systems.
Exactly. Think of it like a virtual microscope. It lets us see these atomic level processes, things that are often just invisible to standard
Too
experiment.
fast, too small.
Precisely. So our goal here in this deep dive is to guide you through the basics, the fundamental concepts, but also some pretty surprising applications of MD.
Showing how researchers tackle everything from, say, a simple protein in water to much more complex challenges like drug design.
Right. Now, getting started with MD simulations, it can feel a bit intimidating. There can be, critical barriers to entry for new users.
I bet. You need some physics, math.
Programming, command line stuff, it's a mix. But we'll highlight how structured approaches, like tutorials, can simplify things, help you grasp what really matters in this complex field.
Good. And our sources for this are actually a set of GROMASS tutorials
Mhm.
designed by experts precisely to, well, demystify the process.
Yeah, they're excellent resources.
So we're going to pull out the most important bits, the key takeaways, so you can quickly get a handle on the power and maybe some of the subtleties of these simulations.
Sound like a plan.
Okay, so at its heart, molecular dynamics simulation is about simulating motion, right? Propagating dynamics.
That's the core idea. It hinges on understanding the relationship between a specific arrangement of atoms, a configuration, and its energy.
And this whole process is driven by these things called empirical force fields,
Right. Which are essentially complex energy functions and parameter sets. They're used to calculate the forces acting on every single atom.
based on where it is relative to all the others.
Exactly. And once you have those forces, you can update the positions of all the atoms over a tiny, tiny discrete time step.
Like a miniature flipbook, showing how the molecules sort of dance and change frame by frame.
That's a great analogy. It builds up a picture of motion over time.
But, while that concept forces, motion sounds pretty straightforward.
The reality is a bit more complicated.
Yeah, the practical side involves a whole complex series of decisions.
Yeah.
You, the user, have to choose so much.
Everything. The starting structure, the specific force field, and there are many. The salt concentration, the integration algorithm, how you control temperature and pressure.
Even just how long to run the simulation for.
Absolutely. And each one of those choices, each decision can significantly impact the quality, reliability, and reproducibility of your results. Get one wrong and
Things can go off the rails.
pretty easily. And this is really where a package like GROMASS comes into its own. It's open source, free, and flexible.
Which is huge for researchers.
Definitely. And it's consistently ranked among the fastest MD codes available, so it gives people the tools to navigate these complexities effectively.
Okay, so what does this look like in practice? Let's say you're building a simulation from scratch, something relatively basic like simulating lysozyme in water. Where do you start?
You begin by generating a topology.
Right, the blueprint you mentioned.
Exactly. It's like the molecule's ID card. It lists all the atoms, their types, their charges, how they're bonded, angles, dihedrals, everything needed to describe it chemically for the force field.
Okay, got the topology. Then,
Then you define a simulation box around your molecule, your protein in this case, and you fill that box with solvent, usually water.
and this is where periodic boundary conditions come in, right? This sounds important.
Oh, it's absolutely critical. In a real-world solution, a condensed phase, there aren't any edges. A molecule doesn't just hit a wall.
Right, surrounded by other molecules.
Precisely. So to mimic that infinite environment in a computationally manageable way, we use periodic boundaries. Identical copies or images of your simulation box surround the central one in all directions.
So if a molecule drifts out one side,
It re-enters from the opposite side, and crucially, atoms near a boundary interact with atoms in those neighboring image boxes.
so it prevents weird edge effects, like molecules just flying off into nothing,
Right.
evaporating into a vacuum.
Exactly. That would be completely unphysical. It simulates an effectively infinite system.
Okay, that makes sense. But it brings up a question. How big does that box need to be?
That's a very important practical consideration. There's something called the minimum image convention.
Okay.
Basically, it dictates that your box must be large enough so that any given atom only ever sees the single closest periodic image of any other atom within its interaction range.
So if the box is too small,
If it's too small, an atom might interact with two copies of the same distant atom, effectively double counting forces. That leads to artifacts, unphysical behavior in your simulation.
got it. And you actually have to think about this even before adding the water, based on the force field.
You do. You need to consider the non-bonded cutoffs your chosen force field uses. These define how far out interactions are calculated explicitly. The box dimensions need to accommodate these cutoffs plus the size of your molecule.
Right, balancing accuracy and computational costs.
Yeah.
So box defined that you fill it with water using like the Solvit program.
Correct. And that program is smart enough to delete any water molecules that it initially places overlapping with your protein atoms. You don't want clashes.
That makes sense. Okay,
Right.
protein, water, box.
Yeah.
What's missing? Ions.
Ions, yes. Most biological systems contain salt, right?
Yeah, sodium chloride, potassium chloride.
Exactly. And simulating under electroneutral conditions, meaning the total charge of the system is zero, isn't just about being biologically realistic. It's often a strict requirement for the methods used to calculate long-range electrostatic forces accurately. Things like particle mesh Ewald or PME.
PME.
It's a very efficient and widely used algorithm for handling electrostatics in periodic systems, but it requires the overall system to be neutral.
So ignoring ions or having a net charge can cause serious problems.
Serious artifacts, yes, especially in complex heterogeneous systems like proteins or membranes. So you add counterions like sodium or chloride to neutralize the protein's charge and maybe mimic a specific salt concentration.
Okay, system built. Protein, water, ions, neutral charge. Can we hit go now?
Not quite yet. Before you start the actual production simulation to collect data, the system needs to relax. This is where energy minimization comes in.
Relaxation.
Yeah. Think about how you built the system. You plopped a protein in, added water, maybe sprinkled ions randomly. There are bound to be some bad contacts, some clashes, maybe hydrogens in weird positions.
Like atoms too close together.
Exactly. High energy configurations. Energy minimization uses algorithms like steepest descents or conjugate gradients to systematically move the atom slightly to find a low energy state. It resolves those clashes.
But this isn't dynamics, right? No time passes.
Correct. Time doesn't elapse during minimization. It's purely about finding a reasonable starting point, a stable, low-energy structure, so that when you do turn on the dynamics, the simulation doesn't just, well, explode.
Okay, minimized. Now are we ready?
Almost.
Okay.
Next comes equilibration. This is where we actually run dynamics, but with the goal of bringing the system to the desired temperature and pressure, achieving a stable thermodynamic ensemble.
Ensemble, like NVT or NPT.
Precisely. Constant number of particles, volume and temperature, NVT, or constant number of particles, pressure and temperature, NPT, which is often more realistic as it allows the box volume to fluctuate.
And during this phase, you often use position restraints. What are those?
Good question. Position restraints are like gentle springs attached to certain atoms, usually the heavy atoms of your protein or solute. They don't freeze the atoms completely, but they penalize large movements away from the starting minimized structure.
Why do that?
It allows the solvent, the water and ions, to relax and arrange itself properly around the solute, which is initially held gently in place. Without restraints, especially with random initial velocities, the protein structure could deform badly before the solvent has time to adjust. It's like nudging things into place carefully.
Okay, so let the water settle down first.
That makes sense. And during equilibration, you need to be aware of the hot solvent cold solute problem.
Uh-oh. What's that?
If you just assign initial velocities randomly and start heating, the solvent might heat up much faster than the larger, slower-moving protein or vice versa. This isn't physically realistic thermal equilibrium.
So how do you fix it?
You often define separate thermostatic groups. For example, one group for the protein and another for everything else, water and ions. Each group's temperature is coupled independently to the target temperature.
Ensuring everything heats up or cools down correctly.
Right. And the choice of thermostat, the algorithm used to control temperature, is also critical. Some older methods, like Berenson weak coupling, are okay for reaching the target temperature, but they do not sample a correct canonical velocity distribution.
Meaning the spread of atomic speeds isn't quite right for that temperature.
Exactly, which can affect properties that depend on kinetic energy. Newer methods, like the Bussy velocity rescaling thermostat, do a much better job of generating the correct statistical ensemble. Same goes for pressure control, choosing the right barostat.
Wow, okay. Lots of details just to get a stable baseline simulation running.
It really sets the foundation. Get the setup and equilibration wrong, and the production data you collect later might be meaningless.
Right. So we've covered the basics for a protein in water. Let's get into some more advanced, maybe trickier situations. What about proteins that live in cell membranes?
Membrane proteins. Hugely important biologically signaling pathways, cell interactions, drug targets.
They're really hard to study experimentally, right? Because they're hydrophobic, they hate water.
Exactly. They like being buried in the fatty lipid bilayer. Simulating them requires quite a bit of special care.
Like different force fields.
Often, yes. You need force fields that have accurate parameters, not just for the protein, but also for the specific lipid molecules making up the membrane. This might involve force field modifications or choosing specialized lipid force fields.
And getting the membrane around the protein must be tricky too.
It is. You often use iterative lipid packing routines. A common approach, like one called inflate GRO, involves placing the protein in a pre-equilibrated box of lipids and solvent, then scaling up the lipid coordinate slightly, deleting lipids that now overlap the protein, running some energy minimization to relax clashes, then shrinking the box back down.
You might have to repeat that.
Often many times. Scaling, deleting, minimizing, shrinking, until you get a well-packed, stable lipid bilayer around your protein without unrealistic gaps or overlaps.
Okay, that sounds involved. And I guess the equilibration is different too.
It has to be. Membranes are inherently anisotropic, different in different directions.
Meaning?
The pressure within the plane of the membrane, say XY, behaves differently than the pressure perpendicular to it, the Z-axis. So you need semi-isotropic pressure coupling.
Controlling the XY pressure and the Z pressure independently.
Exactly. To maintain the correct membrane tension and thickness. Also, lipids move much slower than water.
Right, they diffuse differently.
So you usually create separate center of mass motion removal groups for the protein membrane system and the solvent. This prevents the thermostat or barostat from making spurious velocity adjustments based on the different diffusion rates.
Again, highlighting how the system's specific nature dictates the setup.
Absolutely. You can't just use a one-size-fits-all approach.
Okay, this is fascinating. Let's shift gears again. What if you want to study a process, not just a static structure or equilibrium fluctuations? Like, how does a drug molecule bind to a protein, or how does a protein change its shape? These often involve high energy states.
Right. Transition states that are visited very rarely in a standard, unbiased simulation. You might need to run for ages, or maybe never even see the event happen.
So how do you simulate those rare events?
This is where free energy calculations and using biasing potentials become really powerful. One key technique is umbrella sampling.
Umbrella sampling. Yeah.
The idea is you define a reaction coordinate, some measure of progress along the pathway you're interested in. It could be the distance between the drug and the protein's binding site, or an angle describing a protein's conformational change.
So a path from start to finish?
Sort of. You then generate a series of starting configurations or windows spaced out along this reaction coordinate. And for each window, you run an independent simulation, but you add harmonic biasing potential, like an invisible spring centered on that window's position along the reaction coordinate.
What does the spring do?
It restricts the simulation sampling to stay within that specific region, that window along the path. So even if that region corresponds to a high-energy state, the bias potential forces the system to explore it.
Like holding the system in place at different points along the path, including the difficult high-energy parts, like pushing a ball over a hill bit by bit.
That's a good way to think about it. You run simulations in multiple overlapping windows covering the entire path. Then you use statistical methods like the weighted histogram analysis method, WARM.
The Bennett acceptance ratio, BAR.
Yes, BSR is often preferred now as it computes the free energy difference between adjacent windows with minimum error. By combining the results from all windows, you can reconstruct the free energy profile along the entire reaction, coordinate the energy landscape of the process.
Even though you use these artificial springs, these biases.
Exactly. That's the beauty of free energy being a state function. The final result, the free energy difference between the start and end states, doesn't depend on the path you took or the biases you used to get there, as long as you account for them correctly during the analysis. These methods often involve sampling unphysical intermediates, but they lead to physically meaningful results.
How do you get those initial configurations along the path, especially if it involves pulling something apart?
Often you'd use something like steered molecular dynamics, SMD, first. GROMASS has a pull code for this.
Steered MD.
Yeah, you apply an external force, often via a virtual spring attached to an atom or group of atoms, and you pull it along your desired reaction coordinate at a constant velocity or with a constant force.
Like physically dragging a molecule away from another one in the simulation.
Pretty much. For example, pulling a peptide off a larger fibril, you record the force required as you pull. This gives you a rough idea of the process and, crucially, generates snapshots along the pathway that you can then use as starting points for your umbrella sampling windows.
So SMD to get the initial path, umbrella sampling to get the detailed free energy.
That's a common workflow, yes. It's powerful for understanding binding affinities, conformational changes, barrier heights.
Which leads us nicely into drug design. Simulating protein-ligand complexes must be huge there.
Absolutely critical. Understanding how a potential drug molecule, the ligand, binds to its target protein is fundamental.
But you mentioned force fields are mostly for proteins and standard molecules. What about these often quite complex drug molecules?
That's a key challenge. Ligands, these small molecules, aren't usually part of the standard biomolecular force fields like CHARMM or AMBER, so you typically need to produce a ligand topology outside of GROMACS.
How do you do that?
You often use other programs and generalized force fields, like CGenF for CHARMM-compatible topologies or GAF for AMBER. You start with the ligand's 3D structure, add hydrogens correctly, and then use these tools to assign atom types, charges, and all the necessary bond, angle, and dihedral parameters.
And the quality of that process is crucial.
It's extremely. Garbage in, garbage out. Tools like CGNFF will even provide penalty scores for the parameters it assigns.
Penalty scores.
Yeah, they indicate how well the parameters derived from analogy to existing molecules actually fit your specific ligand chemistry. A high penalty score is a major red flag.
Really?
It means the standard parameters are probably a poor fit and significant manual refinement or reparameterization is required. Ignoring high penalties can lead to completely wrong simulation behavior for your ligand.
Okay, serious caution needed there. And even with a good ligand topology, any other special considerations when simulating the complex?
Well, think about thermostating again. The protein and the ligand are bound, their motions are coupled. So you typically merge them into a single thermostating group.
Right, treat them as one unit for temperature control. Makes sense.
And for analysis, you can look at lots of things. Specific hydrogen bonds forming and breaking between the protein and ligand over time. You can track the ligand's RMSD.
Root mean square deviation, what does that tell you?
It measures how much the ligand's position and orientation change over time compared to a reference structure, like the starting pose. A low stable RMSD suggests the binding pose is stable. If it jumps around a lot, maybe the binding isn't stable or it's exploring different poses.
Useful. Can you calculate, like, the binding strength?
You can calculate things like interaction energies, non-bonded energy, van der Waals, and electrostatic between the protein and the ligand. But, and this is a critical point, that interaction energy is not a binding energy or free energy in the thermodynamic sense.
Ah, why not?
It ignores entropy, solvation effects. It's just one component of the potential energy. It might be useful for comparisons if the force field was specifically parameterized to make it meaningful, but you can't directly equate it to experimental binding affinities. That requires more complex free energy methods like umbrella sampling or alchemical transformations.
Okay, important distinction. Don't overinterpret interaction energy.
Exactly.
All right, one last fascinating concept from the tutorials. Virtual sites. These sound, well, virtual.
They are. They're fascinating. Virtual sites are particles used in the simulation that have no mass.
No mass. How does that work with Newton's laws?
It works because their positions aren't integrated directly using forces like real atoms. Instead, their positions are calculated geometrically based on the positions of nearby constructing atoms, real atoms with mass. Any forces acting on the virtual site are mathematically projected onto these constructing atoms.
Sometimes called dummy atoms.
Yep. Dummy atoms, virtual interaction sites, various names.
Okay, but why use them? What's the point?
They have several clever applications. One is for modeling linear molecules, like carbon dioxide, CO2. A perfectly linear molecule causes algorithmic difficulties for some simulation constraints and integration algorithms because of forced discontinuities if the angle hits exactly 180 degrees.
So virtual sites help avoid that.
Yes. You can represent CO2 using virtual sites for the C and O atoms, whose positions are constructed relative to massless points along the bond axis, or relative to mass centers that carry the actual mass but aren't atoms themselves. Clever. Other uses.
You can use them to represent lone pairs of electrons on atoms, like the oxygen and water, which can improve the accuracy of electrostatic interactions. Or, perhaps most significantly, you can use them to repartition hydrogen mass.
Repartition hydrogen mass.
Yeah. You can transfer some mass from a heavy atom, like carbon or oxygen, to its bonded hydrogens. This makes the hydrogens heavier, which slows down their very fast bond vibrations.
And why do that?
Because the fastest motions in the system, like XH bond stretches, dictate the maximum simulation time step you can use, typically around 2 femtoseconds. By slowing down those hydrogen motions using virtual sites and mass repartitioning, you can often increase the time step to 4 or even 5 femtoseconds.
Without losing accuracy.
If done carefully, yes. It can significantly speed up your simulation, potentially doubling the simulation time you can achieve with the same computational resources.
Wow. So virtual sites are basically a computational tool to maintain physics while gaining efficiency or overcoming algorithmic problems. That's a perfect summary. For CO2, for instance, you ensure the construct preserves the total mass and, critically, the molecule's moment of inertia, its rotational properties, so it still behaves physically correctly even with the virtual sites.
It really shows the level of sophistication in these MD packages.
It does. The flexibility is remarkable.
So wrapping this all up, from setting up a basic protein in water, dealing with membranes, calculating free energies for complex events, handling custom ligands, even using these clever virtual sites, it's clear MD is incredibly versatile.
Vast and powerful, definitely.
But the consistent theme, the real takeaway from all these different techniques, seems to be the absolute need for careful planning.
Couldn't agree more. Every single choice, force field, box size, ions, minimization strategy, equilibration protocol, analysis method, every step dictates the quality, reliability, and reproducibility of your simulation.
It's not just pushing buttons on the software.
Not at all. It's about understanding the underlying physics, knowing the potential pitfalls, reading the literature, validating your setup, and making informed, justifiable choices.
Right. Ultimately, successful MD isn't just about running the simulation, is it?
No, it hinges on that rigorous setup, thoughtful execution, and then really meticulous analysis. It's all about ensuring your simulated data are genuinely useful for answering the scientific question at hand. You can't just run a simulation and hope something interesting will happen.
You need a clear question and a sound methodology to answer it.
Exactly. The complexities are definitely there, but the insights you can gain into how things work at the molecular level are often invaluable, things you just can't see any other way.
Absolutely. This deep dive really drives home how these simulations are pushing boundaries, helping us understand life, disease, materials, all at this fundamental level. So next time you hear about a new drug discovery or some insight into how a biological machine works, spare a thought for this hidden world of atoms and the intricate simulated dance that helps us visualize it.
And remember the nuances. We saw how even a simple metric like RMSD can have multiple interpretations.
Right. Context matters. And how just running a short simulation, maybe because you're impatient or lack resources, can give results that are neither accurate nor precise for certain properties.
It really underscores that deep understanding and critical assessment are vital.
It does. It reminds us that even with powerful computational tools, critical thinking, maybe a healthy dose of skepticism about quick results, is always essential.
Well said.
So maybe a final thought for you, the listener, to mull over. We talked about unphysical intermediates used in free energy calculations. What other kinds of clever constructs, maybe even seemingly unphysical ideas, might scientists come up with in the future to reveal even more physical truths about how our universe works at its smallest scales?
That's a great question. What conceptual leaps are next?
Something to think about as you contemplate that invisible world all around us. That's all for this deep dive. Until next time, keep exploring.